When a content management system relies on a rigid database schema, adding distinct content types creates immediate friction. Expansion eventually impacts a solid brick wall. Traditional module development forces engineers to hard-code discrete database tables and PHP controllers for every single new format they want to support. If a single website needs to run a product catalog, a real estate listing, and a job board simultaneously, the codebase rapidly bloats. Maintaining separate controllers and tables for each specific model creates massive administrative overhead. The xCreate module for XOOPS offers a specific case study in solving this exact bottleneck through dynamic content building. By abandoning discrete, hard-coded modules in favor of a unified meta-architecture, developers can bypass the scaling bottleneck entirely. The system adapts to new data structures without requiring constant database rewrites. To understand how this works, we need to deconstruct three specific technical layers: the relational schema, the object handlers, and the presentation helpers. The architecture relies on isolating the content's context from the storage of its specific data points. xCreate achieves this separation by enforcing a strict, category-driven model. By analyzing how this module handles categories, fields, and values, developers can build a single codebase capable of managing infinite, arbitrary data structures. Mastering this dynamic pattern allows architects to deploy systems that handle changing data requirements while keeping the underlying database foundation stable. The primary rule of this architecture is straightforward. The context of the content must be explicitly defined before any data can be stored. This diagram shows the starting point, the xCreate categories table. This acts as the content bucket, holding structural hierarchy, metadata, and the specific view templates for any given content type. With the context set, we introduce a second table to store the actual content records, regardless of their specific format. Looking inside the xCreate items table, we see it only holds common denominator information. It tracks baseline metrics like the item ID, the parent category ID, publication status, and page hits. Notice what is entirely absent here. This table stores zero custom data specific to the content type itself. There are no price columns, no real estate addresses, and no job titles. Instead, a baseline item record relies entirely on its relational link back to the category table to define its context. This foundational bedrock successfully isolates the where, the categories, and the baseline what, the items, from the volatility of unique custom data. With the baseline record secure, we can now engineer the dynamic custom schema itself. This is the xCreate fields table, acting as the central registry for all dynamic properties in the system. Its primary function is to attach unique custom inputs strictly to specific category IDs. Inside the fields table, the system stores schema metadata. This includes definitions for the field type, Boolean flags for required inputs, and the designated display order. Crucially, this table also stores the logic rules. By housing conditional visibility parameters and repeatable data flags directly in the database, the application layer doesn't have to hard-code validation logic for every new form. This metadata can represent anything from basic text inputs to complex image galleries, or even relational lookups that query other database records. By storing schema definitions as dynamic database rows rather than hard-coded SQL columns, the system permits infinite content variations within a single, stable framework. This brings us to the central engineering challenge: efficiently connecting those static baseline records to their highly dynamic field definitions. To solve this, we introduce the final architectural table, xCreate field values. This diagram maps out the module's implementation of the entity attribute value, or EAV, pattern. The core operational rule here is strict. This bridge table stores one row per field instance. Focusing on the internal structure, we find the value index column. This index handles the sorting of repeatable fields, ensuring multiple entries tied to a single definition are retrieved in a consistent sequence. Next to the index, the zoom highlights two separate data payload columns, value text and value file. This split reflects a deliberate structural intelligence. The system automatically routes raw text strings to one column and uploaded file names to another, keeping string queries fast and file references clean. This specific entity attribute value implementation acts as the engine, permitting entirely arbitrary data to be seamlessly queried alongside baseline item records. Moving up from the completed database schema, we reach the application architecture layer. This split-screen diagram illustrates how the system processes that data. Here we encounter a critical software design pattern enforced by the module, the helper split. Looking at the left side of the diagram, raw database rows flow into the persistence tier. This side is governed by the xCreate field handler. It strictly owns the field metadata, manages all database interactions, and generates the underlying form logic. On the right, we see the presentation side acting as a dedicated adapter. The xCreate fields helper ingests those raw stored values and maps them into shape-consistent arrays, specifically structured for the Smarty templating engine. Decoupling the database definition from the UI display prevents the developer from having to rewrite controller logic for every new front-end layout. By tightly decoupling data persistence from presentation, the architecture guarantees the codebase will not collapse under the weight of unique per-category view requirements. Pulling back, we can now audit this full-stack pipeline diagram as a complete end-to-end system. However, a structural audit reveals legacy bottlenecks. First is a fractured approach to file management, highlighted by these red controller nodes. Modernizing this system requires ripping out those scattered upload nodes and centralizing them into a single upload service. But the most critical technical debt lies in the database layer, runtime schema mutations. Executing commands like show columns or alter table in live request paths breaks scalability and introduces severe performance vulnerabilities. To scale safely, this behavior must be entirely replaced by formalized, versioned lifecycle deployment hooks. Stripping legacy bottlenecks reveals a core operational loop. Step 1, the category node defines context. Steps 2 and 3, fields define the schema, while items store baseline records. Finally, values hold the dynamic data, and helpers shape it for the view. By strictly isolating data definition from data storage, engineers can construct CMS architectures that adapt indefinitely to complex business logic without rewriting the foundation.